So let's start today a cubic equation of state. As I told you, we have so many issues with the variable equation of state, like it doesn't work at high pressure and also in the region of two-phase region. So let's talk about cubic equation of state. So there are thousands of questions, but in our course we have only. So this is the second question of state. So first one is variable equation of state. The second one is the cubic equation of state. So this question I told you it can applicable for high pressure. You can say hall pressure, high, low, and moderate. All pressure. So and it can also applicable for the gas phase and liquid phase. For both. So there are four equation of states, cubic equation of states. Number one is called, I can say A, the van der Waal. We will write down V. The second one is Radlicke-Quank. You write RK. Third one is Sauvé-Radlicke-Quank. SRK. And the last one is Peng-Robinson. We write on PR. Okay. So these two questions are more accurate. Because they are depending upon three parameters: temperature, TR, PR, and omega. Omega is eccentric factor. Now this is TR, T over TC. This PR, P over PC. Where TC and PC are the critical temperature and critical pressures, and you can easily find from the appendix B. So these two and omega also from appendix B. So these are less accurate. Because they are depending upon two parameters, TR and PR only. So if you compare with them, so if you compare variable equation of state with the cubic, then variable equation of state is accurate at low pressure and cubic equation is accurate. There is no general, we cannot make a general trend for, but generally we cannot make a specifically like a it must, this rule is must, but no, sometimes it can be accurate, but generally the at low pressure the variable equation of state is more accurate compared to the cubic equation of state. So we will see them in three different forms. The in pressure form. So we write down these questions in terms of pressure form, in terms of temperature or volume, and in terms of compressibility factor. So there are three forms of these questions, but before then that I want to explain a little bit how we can develop this van der Waal equation. So the van der Waal equation, let's say van der Waal equation, the pressure form is of van der Waal equation is P is equal to RT over V minus B minus A over V square. So this one is the attractive term, and this one is the volume of the molecule. So I already told you the kinetic molecular theory states that the force of attraction between molecule is negligible. When the force of attraction between molecule is negligible, then it means the molecules are moving in any direction and they are hitting the wall very strongly, and also kinetic molecules, so that's why, but it's not in real case, there is some force of attraction. So this is the force of attraction, attractive term you can say, and this is called the volume of the molecule. We can also say excluded volume because we are subtracting. Okay, so this is the volume of the molecule, but kinetic molecule states that there is the volume of the molecule is negligible, or there is no volume of the molecules. So it's also not the case. So if there is no force of attraction, then P measured, of course, the P will be less than P ideal, because when there is no force of attraction between molecules, it will hit to the wall more strongly. So that's why P ideal will be higher than the actual pressure of the molecules, pressure exerted by the molecules. And if we have similarly, if we see the V measured, so if there is no molecule of if you don't subtract this term, then it means again your volume will be ideal volume will be higher than the actual volume, because this is the big value because you are subtracting. So this value V means you can say V real, and so real is V minus VB. So V real equal to V ideal minus B. So if you are subtracting this term, of course this term will be less. Similarly, if the pressure exerted by the molecule on the surface, inner surface of the cylinder, it will be more if there is no force of attraction. So based on that, we will have where A and B are the empirical constants, they are determined by the experiments. So that's why these questions are called semi-empirical. So the variable question is called empirical equation of state. So you can say, you can write here, this is called empirical equation of state. Empirical means which are based on experiments, and this one is called semi-empirical. So because we have these two parameters are based on experiments. So just to then we can have so A and B we are getting from the experiment values. So that's why we can, and we are modifying this from the kinetic molecular theory. That's why we are having this van der Waals equation. So again, R is universal gas constant, temperature, pressure. So we are writing, I just wrote, so based on that we can write all questions in terms of pressure. So there is one general form of that, so if you see here, so what we can do is we can just write on a general form like P is equal to RT over V minus B minus attractive term. You see why I am writing here attractive term. So all so rest of all the questions they are just changing the trajectory term, keeping this terms constant, keeping the trajectory term different, and they are developing different questions like that. So if we see here, so these are the questions in terms of pressure. You can see van der Waals equation of state. I have written where A and B, you can see the units in that form. A and B are in this form. ZC is given. So this is called compressibility factor, compressibility factor at critical condition. Okay, and this is two parametric. So see, I have and go for with the RK. We also see some same question, only trajectory term is different. Then you can go to the SRK. So they have another attractive term. This alpha TR, they have added this one, and you can get it from the table 3.1. So this is the table 3.1, page 98 of your textbook. So this alpha TR, and it's a function of omega. So I told you the SRK and PR are the three parameters, and they are depending on three parameter corresponding states. So that's why we are having alpha TR one more term, and they are more accurate. So see, again the trajectory term is different here, the trajectory term, but this term remains constant. So what we need to do is then, so see, there is another term ZC. Actually there are some questions, these questions are based on, the cubic questions are based on see, is omega is involved in them. Alpha TR is there, which is function of omega. So based on omega, there are some questions which are purely dependent upon ZC. So the question like questions based on ZC, and those questions are like Leaderson. We will not cover that one because it is not in your course, but this Leaderson question is purely based on ZC, and you can see the ZC value, the question based on ZC or Leaderson questions. Okay, question. So you can see the ZC values for each question. They have also given ZC values. These are the constant values for that. So ZC value, the experimental value of ZC are generally range from 0.24 to 0.3. Okay, so generally based on from ZC from 0.24 to 0.3. So if you see among these, so these are the experimental value of ZC. So experimental values of ZC. So if you see this value, the maximum value is 0.3. So all questions are not so accurate compared to experiment values, but the more closer value is this one, 0.3. So this shows that the PR among them is very, very accurate compared to the rest of the cubic question of states. Okay, so you see its ZC value is close to 0.3 at the extreme value. See, this is extreme 0.3 value. At least is near to, but the rest SRK is 0.33, ZC for RK 0.333, because they are same group, so they are getting same values. And ZC van der Waals, they are getting 0.375, where far high value than. So it means this is van der Waals is the least accurate question. So because this was the first question developed by the van der Waals group, that's why after that the people are modifying this question. I told you they just modify the attractive terms and they are getting more and more. So they are, and now they have more than 1,000 questions and people are developing, but we cannot generalize which equation is more accurate. We cannot say authentically that this question is more, because for different conditions question will be, they behave differently, and they and we can apply different questions at different conditions of, but these questions we can say only for hydrocarbons. But when for hydrocarbon, penguin is very accurate compared to the rest of. If we are taking same components and taking all the hydrocarbons, then penguin is more accurate than the rest of the questions. But if you go to the but if you talk about other questions like if you talk about other questions like other components like any polar components or any other polar like ammonia, and then we have to verify, we have to check depending on what temperature which question is more accurate. So all these depend on these kind of circumstances. So you can also see everything in my slide as well. So then let's see what we can do is, so I told you there are three forms. So the pressure form I have already written and I will share with you. You can also see in my slides as well. Then let's talk about the volume form. So volume form, we have one volume form and one we can talk about the Z form. So for the gas phase, I will add both here. For the gas phase, volume form is RT over P plus B minus AT over P V minus B V plus epsilon B V plus sigma B. So this is for the gas phase. Volumetric form is like that. And compressibility factor, another form is in terms of compressibility factor, where 1 plus beta minus q beta z minus beta z plus epsilon beta z plus sigma beta. So here the initial gas will be, so here the initial gas is ideal gas value like variable, like V equal to RT or P. So this is your initial gas. When I start problem, we are just trying to solve by giving initial gas. Maybe the value is close to initial gas, okay, it will work. But if it's not, then of course. So here the values of epsilon and sigma you can easily calculate. You can easily find from the appendix from the table 3.1. So here the initial gas, again we take the initial gas Z equal to 1. So